Today what we're going to do is finish up the garage door application. Again, I love this application. There's just a lot you can do with it. I do encourage you to go off on your own. You have enough knowledge now and experience that you can think up of other things to do with this logic to make the garage door do something different. You know, you can add your own touch. Remember, the goal of this part of the training, this part of the learning, is for you to take an idea, put it into logic, download it, and see it do what you expected it to do. And of course, if it doesn't, you'll figure out why it's not doing what you expected. You'll go back and you'll edit the logic, and then you'll try it again. And eventually, you'll come to the point where most of the time, when you convert your thinking, your logic, into ladder logic diagrams, that the result will be very close to exactly what you expected, if not exactly what you expected. Now, this particular part of the project involves the introduction of timers. The thing you need to understand about timers and counters is they both count something. Counters, which we haven't gotten to yet, they count events. Timers count units of time. Now, y'all know that computers have a clock, that when a computer executes, the operating system executes internal programming, it does it on clock cycles. So let's say that the computer is going to add two numbers. It'll load a value into register A on one clock pulse. Then it'll load a value into register B on the next clock pulse. Then on the third clock pulse, it will use logical functions against the binary bit. So remember, each word, each value is represented in binary. So when you look at two binary words, it's just ones and zeros. So you've got units, 2s, 4, 8, 16, 32, and so forth. So when you work with those bits on those two words, you're just using and, or, nor, whatever at that bit level, but that's all done in sequence with a clock pulse. Execute step 1, step 2, step 3 on a clock pulse. Those clock pulses, of course, are in the megahertz range. So the PLC, it's a computer. It executes everything step with the clock frequency. So a timer is going to count units of time. Now, the newer controllers, processors, typically count in thousandths of a second, milliseconds. Some of the older stuff gave you the choice of thousandths of a second, hundredths of a second, tenths of a second, or in seconds. Now with the Micro 800, you have at least a thousandths of a second. Typically, I always use milliseconds because that gives me more resolution if I want to adjust the time and I want to make it really tight. If you work in seconds, then the difference between 1 second and 2 seconds or 3 seconds, that's a big jump in the processing world. So milliseconds is what I use, and you're going to see that it's going to be, even though you put in milliseconds, it might be displayed as seconds and milliseconds, minutes, seconds and milliseconds, but timers count units of time. So now for the garage door application, as you well know, you have a garage door light, and that light is on anytime the system is disturbed. And there's a variety of ways that you can disturb the system. By pushing a button, breaking the beam on the photo eye, there's all manner of ways that you can disturb the system at rest. And the system can be at rest in 3 different ways. It can be all the way down at rest. It can be all the way up at rest. It can be halfway up and down at rest. And remember, the system should not know the difference between halfway up and halfway down. So if you stop the garage door and it's right in the middle between all the way up and all the way down, the system doesn't know where you were going when you stopped it or when you tripped the photo eye. Now, the way we did the safeties, yes, if you trip the photo eye, then it's going to stop it if it's on the way down, but not if it's on the way up. That's a matter of preference. You could program it so it stops it, period. If you break the photo eye, it just stops. Okay, for a matter of convenience, we don't. Now, me, when I sometimes leave my garage, probably because I'm lazy, I don't know, or maybe I just like the challenge, I will hit the button on the wall inside the garage to close the door. I'll run to the garage door, and while it's coming down, I will, so to speak, hop over the optical path of that photo eye so it doesn't stop the garage door from coming down. I don't know. Kid, I'm just like a little kid. Okay, so let's get into this lab project. And we're also going to consider some other variations in programming, like latch, unlatch, which is set, reset, versus seal-in logic. Now remember, seal-in logic is the best. When you start using latches, then you have to unlatch the whole world, because it's easy to latch something in Cincinnati and you're in Chicago when you realize that you left it latched. Now you got to figure out how to unlatch it. That just means that this stuff can get spread out all over your program. With a little tiny program like this, it's not a big deal. So let's have at this. We start lab project M6D, first timer, by demonstrating how to add a timer into a rung. Now you can grab timers from this menu up here by going over until you find timers, timer counter right there, and we're after a TON, on delay timer, output on after time reaches preset. So this is a nice menu up here, but in the manual we actually went to the toolbox and we grabbed an instruction block and then drug it in and dropped it into the rung. Then you could scroll down, or you could just type in TON. The only instruction blocks that come up are these two. So we pick this one. You can also name it right here. So we'll leave it TON1. It gives you, notice it says instance. Okay, we'll just keep the default name. Okay, now you have a TON. This is the same thing you would have realized if you grabbed it from up here, with one exception. It comes up TON_2. It knows you have a TO1_1, so it automatically gives you the next incremental numerical name. I'm going to delete this because I don't want that in there. Remember, one of our priorities is to demonstrate the unapparent nature of these instructions aside from the obvious, more apparent nature. So we had you build this as is and download it. Turn on your simulator. I say turn on, I should say open it or create it, then turn it on. Power button. We're powered up and it's running. Now save, download, and we are right there. As soon as this downloaded and went to the run mode and executed, because the rung is unconditionally true, the timer was enabled right away, and because there is no preset value, the preset value is considered 0. So the output of the instruction is immediately true because the elapsed time equals the preset time. If the preset time is 0, then the elapsed time is 0. Now we could put in a preset time of 0. We have no variable in there right now. We're going to go back offline and add some more to this. But what I wanted to point out is it will let you get away with this, but this timer instruction or timer data type instance is actually TON_1, is for the most part useless. So let's save and go offline. We're going to add a direct contact. We can grab it up here or over here. Direct contact, drag it over here and drop it. It comes up local variables. That's by default because we created a new project. In some cases, we may want to add this in the local variables, but we're going to go to I/O and we want digital input 0, which is right here. If you click anywhere off the screen, don't hit the X here because that will eliminate the toolbox from your workspace. And to get it back, I'll just show you that real quick. I'll exit out. See, it's gone here now. We can go up to Windows. reset window layout, and it restores the default. Now you got the toolbox back. Also notice that we don't have the micro 850. Okay, so we added this input. Now we want to grab a direct coil, drag it in, drop it, IO, micro 850, and we want output 0. And there's our logic. What we don't have is a preset, so let's add a preset. You can add it in this field. And timer data types, or time data types, always begin with a T and a pound sign. Then we can put in seconds or milliseconds. I always use milliseconds to kind of hold the format from RS Logic's 5000s. I had you put in 1500 and then MS. You designate the time base, 1500 milliseconds. That's your preset. Now we have you save it and download. And then we had you operate input 0. So we bring our simulator back up, turn on input 0, and you can see that it's scrolled, or it incremented from 0 up to 1 second, 500 milliseconds. Now notice that I put it in as 1500 milliseconds. It displays it as seconds and milliseconds. You can see the preset value here and the cumulative value there. So if I double click on 0 down here, input 0, it's going to reset it, and then it increments again, and after 1.5 seconds, output 0 comes on. Does the output change state instantly with the change in the state of the input, regardless of the TON instruction between the two? No, because the Q output from the TON instruction goes high when the elapsed time is equal to or greater than the preset time. In this particular, turn your switch on until you see the elapsed time field incrementing, and then off quickly. So off. Now I'm going to turn it on and then back off. And you see that I turned it off before the elapsed time reached the preset. And because I did that, although the input was on for almost a whole second, the output never came on because the input condition went false and it reset the timer. Reset the elapsed time back to 0. The preset doesn't change. It's fixed based on your configuration. So if you let the input go false or off, false in or off, then it's going to reset the timer. And it's never going to time out unless you leave on 0 long enough for it to increment until the ET equals the PT, then the output's going to go on. Does the output ever energize if you do it in less than 1.5 seconds? No. Let's open the global variables, the local variables, unpin it, bring it over to the side here, expand TON1. I'm going to operate the logic again. I'll bring up the rung. Okay, so now we have our simulator, and I'll move it up so you can see them all much more closely. So watch over here. The preset doesn't change, but notice it's grayed out. So the things that are going to change on the fly would be the ET, not the PT. So let's turn this off, and you can see that these checkboxes all went empty, and the ET went to 0. So let's turn it back on and watch in the local variables. Real simple. Timers are simple. We had you close the project for the timer and open up your previous project for the garage door. Of course, you need to open the simulator. We had you rename, or rather put in a different tag here. We don't want to change both push buttons pressed. That's a tag right here. We want a new tag. So we'll just bring up the field and type in safety_interrupts. That is a new tag or a new variable. So we go to variable selector, and I'm going to put it in the local user global variables just to keep everything in the same place. Okay, we made that modification. In the manual, I specify between editing a variable and creating a new one. So now let's go to our global variables, scroll down, and see we still have both push buttons pressed. So if we go back and look at our sequence, see both push buttons pressed, and this is safety interrupts. That's why you have to be careful what you're doing. So I actually did it both ways. I'm going to go here, open that up, and I'm going to type in SA, hit enter. Now the logic is correct. If I had edited both push buttons pressed, go back to global variables, see we still have both push buttons pressed. So where is our new one? It's down at the bottom, safety interrupts. It will appear up with this group after you've done some refresh with the screen. We're not going to do that right now. Now what I want to do here is, here's where I could edit the tag. Okay, so I could have gone here and edited the tag name here, safety interrupts, and not changed it in the logic. In other words, I created a new one in the logic, and here I went and edited the old tag name. So make sure you keep track of what you're doing. And because I created a new one right here, it did not change this one automatically. If I had edited both push buttons pressed, then both of these would have changed because I edited the tag name that these two instructions were associated with. But what I did instead is, and a lot of people do this by accident, is they think they're editing the tag name right here by selecting it and typing in something new, when in reality they're creating a new tag or variable name, and it's not assigned to this instruction over here. I hope that's clear to you. Next we had you add a rung of logic. So we're going to scroll down. We're going to bring a new rung down. You can see we're running out of vertical space here to show all the logic in one screen. And what we did is we ORed some instructions together with another instruction and created a new rung. Here's our new rung, just the logic. Now you could put the tag names or variable names in as you go. I like to do it right on the logic. This one is the stop push button. And the moment I punch in IN, I typed in lowercase, but it came up with whatever was in the tag or the variable database that begins with IN. I wanted input 0, so I just hit enter. This one is the up push button, which is input 1, and the down push button. Now I have variables assigned associated with these instructions, but not this one. This one is going to be associated with a timer, an element of a timer data type. So I have to add another rung yet. I need to put in some conditions and then add the timer instruction. I need a preset. We have all the logic in here. We have one last thing to do, and that is we have to attach a bit from this instruction, this data type. This, in the instance of this Pt1 data type, is controlled by the logic in this rung. So we want an interaction between one of the bits and this timer data type and this rung. And to do that, we go up here to the field and we type in light, LI. That gives us light on, delay off. Then put the cursor after it and hit the decimal point, and it pops up the elements of that instruction. Now this is something that's still kind of awkward if you're used to using RS logics. You have to pay particular attention. I'm going to delete that. I'm going to go back to what it was. If I had done it right the first time, and I will just delete the whole thing, then I will type in LI, and if I click it once, then once here, you have to reopen it, put in the decimal point, and then pick Q. Now your logic is ready to save and download. And in the manual, I ask you how you would state rung 3 logically and the other rung. This rung says if not stop push button or up push button or down push button or not photo eye safety or output 02 is on and that the timer's not done, then output 2. In other words, turn on the light. So if the timer's not done and any one of these conditions is true, you can AND any one of these because they're ORed, this or this or this or this or this, and that, then this. Any one of these, when the timer's not done, will turn on that light, which means this bit's going to be true. So this is going to stay true as long as that's on. The only thing that can interrupt it is if the timer reaches a point where the elapsed time equals the preset. So what keeps the timer going? Remember that we demonstrated in the first lab for timers is that as long as the input is true, this keeps accumulating until the ET equals the preset. But if anything interrupts the true end state to this instruction, then it clears the elapsed time and it starts over again when the run goes true again. So if the light is on and the stop push button is on, meaning not pressed, you're not pressing the up push button or the down push button, and the safety photo eye is not tripped, then the timer accumulates. If it accumulates for 15 seconds, then this will go false, drop out the light. This will now be false, and it'll stay that way until one of these goes true again. Because remember that if the light goes out after that 15 seconds, then this is false and it resets the timer. So this is false until the light goes back on. And how the light goes on, okay, so remember the timer's cleared because this went false. It cleared the timer at the end of 15 seconds because the light went out, right? Light went out in the garage, cleared this. So this is now true because the timer's not timed out. So if any one of these four conditions occurs, then it turns on the light. Now this is true, and even though one of these disappears, in other words, you bump the down button and the light went on and you haven't touched the stop push button up, down, and you haven't blocked the photo safety eye, then this is going to stay true as long as the light's on until it times out, and when it does, this goes false, light goes out, and this goes false. Simple enough. Let's save and download this. Notice that the light went on right away for a real simple reason. We're using the simulator. We don't have the benefit of hard-wired I/O. So we have two things going on. The safety photo eye says it's blocked, and it says somebody's holding down the stop push button. Well, we know that's not true. We have to go turn on inputs 0 and 3. Okay, now you see the timer's timing out, 2 seconds, 3 seconds. The light is on, and when we hit 15 seconds, then you'll see what happens. The timer's timed out. The .Q bit for the timer is going to go on. It goes false, and then it goes back true again instantly. So this goes false for one program scan. So the first program scan that this is false, that turns off this. That way the next scan around, this is not true, so it can't continue. So this went false on one scan. On the very next scan, because the light is now out, then this rung is false, and it resets the timer. It all happens so fast you can't see because it happens in 2 scans, which is less than a millisecond. In less than a thousandth of a second, this all takes place. Now, if I go bump anything, for instance, I'll drag this down so we can't see the outputs, but we can see the inputs. I'm going to double bump the safety photo eye. Now see, the light came on, and we're going through our timing cycle again. So any interruption in the stop push button, up push button, down push button, or the photo eye safety, the safety photo eye, will start this overhead light sequence. Now you can modify this to your heart's content. You can make the time longer. Typically, when I'm testing something like this, I would only make it 2 or 3 seconds, just long enough so I can see that it works. Now, something extremely important that I want you to notice. Did you notice that the conditions that control the light going on, which is input 0, 1, 2, 3, and output 2, are also represented in this rung down here? I don't have them in the exact same order. I could put them in the same order just to make it more clear, but it doesn't need to be. So these 5 bits in memory and these 5 bits in memory are the same bits. Notice that the stop bit uses the opposite condition as well as the up and down in the safety photo eye. So this bit says that the light is on, and if the light is on, then start the timer. If these conditions are in the opposite state of these. So see, this is true if off, stop push button, true if on. True if off, true if on, up and down, true if off, up and down, true if off, photo eye safety, true if on, photo eye safety. So notice that we flipped the state of the bits and we went from or to and. That's something for you to consider and ponder over. The logic is at rest. How many conditions can trigger the overhead light? 4. 3 push buttons or the photo eye. Change and maintain the state of any of the input devices to initiate the overhead light. So in other words, let's block the photo eye. Okay, that's easier. We could send it up or send it down, the garage door. The problem is then we got to, scroll up to the top there, and we should operate the limit switches so they match, etc., etc. So the photo eye is blocked, the light is on, and it stays on. We turned on the light, but we haven't started the timer. This is the important thing. As long as the photo eye is blocked, or you're holding down a button, the light is going to come on and it's going to stay on indefinitely. Then if you change the condition, in this case we're using input 3, we could have done something like this, the push button. See, the light's on, but that made this go false and reset the timer. So we don't get the delay until we have taken our hands or feet out of the photo eye, our hands off the buttons, and our feet out of the photo eye, or objects out of the photo eye. Then the delay starts, and when it's done, then the light goes out. Very simple. Okay, with any of the 4 ORed conditions maintained, does the overhead light illuminate? Yes. Does the light remain on? Yes. Is the timer accumulating or incrementing during that time? No, not if you turn off the photo eye. See, it's not incrementing. We'll unblock this photo eye. It's going to increment. Let the logic time out. Does the light go off? It will. Is the logic back at rest? Yes. Logic's back at rest. Initiate the overhead light again, but release the trigger immediately while watching the ET elapse time. Toggle any of the 4 inputs to the opposite state and back again. Repeat this interruption, the timer accumulation several times until the behavior becomes clear to you. Does the ET go back to 0 each time you do this? Yes. Why is it unlikely that you would see a accumulate of 0? The screen doesn't refresh, plus persistence of vision. Something else I will point out down here, you see the little blue links of the line right there? They're blue, which means false. If I turn the light back on, and I can do that by double clicking on 3, see, now the rung's true, so these show red all the way through. This is for your benefit, so you can see that the rung is false, but the instruction is true. Now you're thinking, well, now I can see the whole rung. Why would I need that? Well, you might be looking at a wraparound, a folded, a big fat long rung, and you can't see the whole rung on the screen. But if you see that little blue piece before a true instruction, you know that the state in from somewhere earlier in the rung is false. There's the culprit right there. Now I'll turn the light back off. I'm sorry. I will unblock the photo safety eye, and instead I will push the stop button. Now you can see that little piece right there is red, but then the rest of them are blue. Let's go down and do input 2. You see red, 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 blue. So you got true coming in and false coming out. A few questions in the manual. Does the ET go back to 0 each time you do this? Yes. Why is it unlikely that you would see an accumulate time, an ET of 0, screen refresh, plus a little condition of your human eye? Is the overhead light illuminated from the time you release the initiating condition until the timer timed out, or from the time you initiated the condition? Both. Is the delay caused by the first action or the last action? The delay begins at the end of the last action. Last touch on a push button or blocking the photo eye initiates the delay. Now we're going to go offline and change the direct coil, and we're going to use what we call latch and unlatch, or set and reset. I'll bring this puppy back up here, and I'm going to save and go offline. Now when I save and go offline, I disconnect. This guy's still running. We turned on input 2. Let's turn that back off, and you can see the garage light stays lit, output 2. Now I'm going to unblock the photo eye, and after 15 seconds, output 2 should go off. So even though we disconnected, the controller's still out there running, which in this case is actually a simulator. But the goal of the group that develops this software is that this simulator behaves 100% like the controller that it's simulating. So now we're offline. We know how this logic works, and we are basically controlling the light from this logic right here. The timer intercedes right here. So if the timer's not done, then we have a true condition here. If it's done, then we have a false condition here. So we're using the timer timing out to release the seal-in from this rung. Now we're going to use set and reset. So I'm going to go to the toolbox and I'm going to grab a set coil. It's not going to let me pop it in there because I've already got something in here. So I'm going to have to delete this first. Then I'll just drag it down from up here, because the one thing I don't like about the toolbox is it blocks the view. So we're going to go to IO. We want out 2 with a set. Now we don't need the seal in any longer, so we can delete that. And now we need another way to reset it, so we're going to grab a reset and put it here. And we're going to use this to reset. So we click there, type in, and there we have it. So let's, we don't need this either. Save and download. Let's demonstrate this. I'm going to scroll down, or rather I'm going to have to push this up, pull this down. So this circuit or this logic is at rest. Okay, now notice that we eliminated everything to do with the timer. We're still using the Q, but it's executing a reset of the light. An OTE, direct coil, has a true and a false execution. When the rung goes true, it turns something on. When the rung goes false, it turns it off. The set and reset instruction each have a true execution and no false execution. If the rung is true, the set instruction turns the bit on. When the rung goes false, it's silent. It doesn't do anything. The reset instruction, when the rung goes true, it turns off whatever bit in memory it's addressing. When the rung goes false, it doesn't do anything. These follow the idea of a latching relay. A latching relay, electromagnetic switch, energize it and it pulls contacts closed. Some open and some closed, right? Depends, normally open, normally closed. When you de-energize it, the contacts go back to their at-rest state, their normal state, normally open, normally closed. A latching relay has 2 coils that are energized separately, never together. When you energize the set coil, or the latch coil, it opens the normally closed and closes the normally opens. And it stays that way. There's a mechanical dog. It's a little catch. When the contact armature comes down, it slides over a ramp on a flexible dog or notch, and it holds it down. So when you remove the power from the latching coil, the contacts stay in the energized position indefinitely. Then you have another coil that pulls the dog back and releases the contacts to go back to their normal state. So the unlatched coil pulls the dog back to release the contacts that were pulled down when you energize the latching coil. So set, reset, latch, unlatch. That's where that all came from. So let's operate this. Right now it's at rest, lights off. So let's just interrupt the photo eye. Okay, I interrupted it. Now you can see I let it go right back to false. But this stays on because when this rung went true, it told it to go on. And it stays on until you turn it off by some other means. You can see when this was true, it timed for 15 seconds. When Q came on, the output came on, then this instruction executed and turned off output 2. Real simple. Now, you're probably thinking, well, looks like a much easier way to program. It is, much easier. However, you'll find that in the industry, using a lot of latches and unlatches, whether you want to call it set and reset or latch and unlatch, is highly frowned upon because the set and reset rungs can get separated to different parts of your program. And you can see here what turns on the light, what sets the bit, but you can't see unless the reset rung is right there with it. You can't see what resets it. Plus, With the other logic, it's easy to see what turns it on and what turns it off. And as a matter of fact, in the main rung, which was rung 3, you knew what turned it off because there was a true if off, light on, delay off timer not done bit. So everything that controlled the light was in that one rung, so to speak. And if you wanted to see what controlled the light on, delay off timer, you could just cross-reference it and go right to this rung. Seal-in logic is the easiest to troubleshoot, but the most difficult to program. You really have to have your thinking cap on and using your head for something besides a hat rack in order to do seal-in logic. Latching is easy. And if you start out in your career doing a bunch of latches and unlatches, if that's the only way you get it done, that's how you get it done. On rare occasions, I will use a latch and unlatch, usually if I want to maintain something during a power cycle or a mode cycle. Because with most controllers, when you cycle, we'll just do that for grins. We'll see how this one behaves. So let's get this puppy going again. We're timing, right? The light is on. So let's go down here, a program mode. Okay, we're in the program mode, right? See, we're not in the run mode. I'm going to go back to remote. Now I'm going to go back to run. And back to remote. Notice that we didn't lose the state. We might have lost the start of the delay. In other words, it's starting over again. Another 15 seconds. But the light stayed on. Now, the light didn't actually stay on in the garage, but the bit stayed on in memory that controls the light. So as soon as you went back to the run mode, the light came right back on. So that's the difference between set reset and just using an OTE or a direct coil. If you want to maintain that bit during a power cycle or a mode cycle, then you want to use this set and reset. And there's other ways of doing it. You can always constantly save the state of the outputs. That's in another lab project way down the road, where you are constantly saving the output image. And so if the logic stops executing, then the last image that was saved before it stopped executing is still there. So when you start back up, you can always go and move that last image, snapshot of the outputs, back into the output image, and away it goes. So let's shut this puppy down, save, and disconnect. One other thing that I had you do in this project before you were done is had you verify that your garage door logic matched what we have here, and then save it and go offline. As if you're doing the panel view 800 projects. In the third manual, not part of this course, but if you are doing that, because you could be doing this course and have the third manual, have a panel view 800, and you could still be doing the panel view 800 projects. We're just not discussing them in this course. You want to make sure that logic is working correctly, because when you go and create your screens, the screens are going to interact with all these bits in this program. Okay, that wraps it up for the garage door application. I hope you enjoyed it. We did some interesting things in how we controlled the disturbance to the system to control the light as far as what keeps resetting it. In other words, the timer is set for some length of time to keep the light on. But if you keep interrupting the enable on the timer instruction, it resets it and it never gets done. So even though you start the timer accumulating, if you touch a button, or if you break the photo eye beam, it starts the time over again. So as long as you keep disturbing the system, we want to keep restarting the delay on turning that light off. Like I said, if you want to, at this point, you can go off on your own and play with it a little bit. I would take, this is your learning opportunity. I guess what I'm saying is I'm encouraging you to squeeze every drop out of this experience that you can get before you go on to the next thing. In the next lecture discussion, we're going to talk more about timers. We did something interesting that we haven't done before in our manuals, and that is we introduced the concept of a timer data type and a timer instruction, and we immediately threw it into an application, which was really good form. Now, all the instructions up to the timer weren't very complicated. You know, truth on, truth off, energize output, you know, set, reset, direct coil, direct contact, all straightforward. Another thing that you should walk away with from this garage door application is a sense of logical priorities. So if you could name the single highest priority in this system, you would probably come up with one or two things. The first would be that if the garage door is on its way down and you interrupt the optical path of the photo eye, that the whole thing stops and it can't restart again until you reset it. Or if somebody's playing with the buttons up and down, that it stops the system and keeps it locked out until you reset it. So when we look at multiple rungs of logic and you find the decisions that one rung makes, in other words, the final, if you want to call it the output instruction on that rung, if that bit is being examined truth on, truth off in another rung, that means that the logic is now interdependent, which this was all the way through, mostly between going up and going down, but also between other disruptions in the system. That is one of the biggest things that you should walk away with, is this relationship of how the decision of one rung affects the decision of another, or prevents it, inhibits it from turning something on or turning it off. Okay, we'll see you in the next lecture. I'm training myself not to tap on the table because the microphone is sitting on a stand and it picks up the vibration, and it's much louder coming through vibration into the microphone than it is the sound from the table. So I apologize for that, and I'm going to train myself to stop tapping on the table. Thank you.